today's presentation that we picked up on, started yesterday. Okay, so we looked yesterday at powers, how you can shorthand write things. Like instead of writing 3 times 3 times 3, you can write 3 to the power of 3. Or instead of writing 10 times 10, you can write 10 to the power of 2, which means 10 squared. Today, we're going to continue that, but we're going to look at it going the other way in what are called square roots. Okay? So, sure, 10 squared is the same as writing 10 times 10, which would calculate to be 100, right? That's what 10 times 10 would be. What square roots do is they start at this point and they get you back to where you were here on the 10. Now, square roots are very difficult to do in your head, which is why this is basically a calculator-based concept here of a square root. Okay? Here's the way you can visualize it, right? If we have a square, a perfect square, we know that each side is the same length. I know that the area of this square is like 100 units, whatever that unit might be. So if the area is 100, what I'd know is the length of one side of this is 10 units. Right? Because we know area is one side times another side. I hope at least someone has taught you that at this point. So you know that this 10 times this 10 would give you 100. And 10 times 10 would be the same as saying 10 squared. Okay? So in doing square roots, we're kind of going backwards. And square roots use this symbol to represent the square root. You're going to find that symbol on your calculator. It's called the radical sign or the root sign. Okay? And you can use it to calculate square roots. So I'm going to show you how that goes. Okay? Now, the thing about square roots is they typically represent the positive answer. Because although 10 times 10 equals 100, negative 10 times negative 10 also equals 100. So when you think of square roots, think of it as just the positive answer. Right? So like that's true. The square root of 100 is 10, because it's the reverse of the process. 10 times 10 equals 100. So it's going the other direction. But I could also say that's true for negative 10, right? Negative 10 times negative 10 is also 100. So the answer could be both positive 10 and it could be negative 10. So when you see that square root symbol, especially here in grade 9, it represents the positive answer, okay? It represents the positive square root. Another name for that is the principal square root, is what they call that, okay? So yes, the correct answer is it could be both positive and negative 10. But what I'm talking about when I show you a square root sign is don't overthink it. It's just positive 10. Okay. If I wanted it to be a negative square root, if that was what I was hoping for, or if someone who written a question that wants it to be negative, they would put a negative sign on the square root, which would say, you could ignore that and just say, well, what's the square root of 100? It's 10, but now I'll bring the negative sign back to put it in the answer. Okay? Now, this is a calculator activity, right, for the most part. To calculate a square root, you don't necessarily know how to do this mentally. Although maybe some of you could figure out what the square root of 144 is. Think about what it could be. 2 numbers multiplied by each other. What would the 2 numbers be?
12.
Right, it would be 12. Okay? But not every number is going to be able to do that in the top of your head. It just so happens that maybe you've got a good grasp of your multiplication tables. But this is how, again, you're going to do it on your calculator. So again, a bit of an exercise. Get used to your calculator so that you can incorporate that key into solving the problems, the square root key. Okay. This isn't really something we're going to do in the grade 9 course, but just as a look ahead. One of the things you're going to be doing, especially those of you going into, say, the pre-cal or the applied math in the grade 10 and 11 course, is you're going to be graphing, putting answers on a graph. And you can see that 2 squared is 4, right? 2 times 2 is 4. 3 squared is 9. 3 times 3 is 9. 4 squared is 16, right? 4 times 4 is 16. But some numbers, like 2.5, won't have, like, its value will be somewhere in that range. If you were to connect the dots of how this looks, it creates a shape called a parabola, okay? This is just sort of showing that square roots create a different kind of math system that's a little more complicated. But at the grade 9 level, generally what you're going to be doing is just calculate them using your calculator. Okay? Okay. Some square roots don't work properly. Like, what's the square root of 2? What times what gives you 2? And the answer is, there isn't a set number that satisfies that. What's the square root of 3? There's no real number that if you multiply it by itself, it becomes 3. So when you punch these in your calculator, and let's try that. Could someone, let me just put the lights up here for a second. If anyone has a calculator, give it a shot right now to calculate the square root of 3. And I'm going to try it on this calculator right here. So one of the things you're going to have to try and find is where is that square root key? Now, in some cases, like this one, it has the square root symbol with a little x underneath it. Okay, so for that one, I'm going to press the 3, and then I'm going to press the square root key. And I'm going to get the answer 1.732050808. And it's run out of room at this point. This is the calculator making an approximation as to what that number is. Because in reality, it could keep going. There could be more decimal places. There could actually be an infinite number of decimal places at this point. And it's not like a number repeating. It's not like 0.6 repeating. It's not the same number repeating. It's varying the number. Okay, so if you get a chance, try that. Try the square root of 2. Square root 2 equals, oops, forgot to clear it. Square root of 2, 1.414213562. So can anyone think of another number that would not generate a perfect square root? What's another? Someone said it over there. What was it? 5. Yeah, 5 would be another example. Okay? Now, what that means is you had these numbers known as rational numbers. What we now actually have is square roots of these numbers are actually called irrational numbers. Okay? And they are kind of a whole set of numbers outside of the ones we talked about before. So you have those natural numbers. That was when you first learned to count 1, 2, 3. Then you had whole numbers, which included 0. So 0, 1, 2, 3. Integers, which included negative numbers. Then this unit's been about rational numbers, which included all those numbers plus fractions and decimals. And now we have a whole branch of numbers called irrational numbers. That's a whole other branch of numbers. Good news, in grade 9, you don't really need to focus on this. This is just sort of thinking ahead a little bit. Okay? At this point, you're kind of just doing, again, like I said, calculation type activities with square roots. But it's something, again, to think about, that there are these numbers outside of the numbers that you'd normally think of. Okay. So square root of when a square root of a given number is multiplied by itself, the product is the given number. So for example, the square root of 9 is 3 because 3 times 3 equals 9. So square root of 9 is 3. Okay? Don't overthink it. It's kind of the reverse of the squaring it. When you multiply a number by itself, it generates a square. And if you take the square root of that number, it goes back to the original number. Okay? Here's another way you could visualize it, diagrammatically, or in a diagram. Okay? So this is the square root of 16. Okay? Now what I mean by this is I have 16 squares filled in. Right? 16 squares of those are filled in. What would the square root of it be? Back corner. What is it? 4. Right? How would you apply that to the diagram? How does 4 apply to this diagram? How? How does it apply?
It's 4 times 4 by 4.
Right. So 4 is the length of a side. Right? This is a perfect square. And 4 is the length of a side. Okay? Now, it's shaded slightly differently, but this is 25 squares filled in. What's the square root of 25? 5, right. And you can see that same way. So now you can see these are perfect squares. They square perfectly. But I could also use that diagram to estimate what would be the square root between 4 and 5. Well, as you can see, it's not a nice set number. So sure, this is 4. Square root of 16 is 4. And the square root of 25 is 5. So what's the square root of 4.5? Well, it would be that black dotted line, which you can't really count the sides. It's like 4.5. If I squared 4.5, I'd get close to 25 or to that number. So it's kind of sometimes a way to grasp it, right? Okay, you could also do this if you think of decimals. This could represent the square root of 0.25. And you could also use it to estimate a square root between 0.5 and between that and 0.6. Okay? A perfect square is the product of two equal rational numbers, right? So you pick any two rational numbers, 6 and it's equal, 6. Multiply them together, you get a perfect square, and a perfect square you can find a perfect square root of. Okay? Question?
No, I was just going to say that 6 times 6 is 36.
That's correct, yeah. Okay, so the number 0.25 is a perfect square because it can be perfectly squared into 0.5 times 0.5. The fraction 9 over 16 is also a perfect square because the numerator and the denominator can both be divided into two numbers that when multiplied by themselves creates 9. Okay? Same with 16. We know 4 times 4 equals 16. 3 times 3 equals 9. But if I had 3 over 16, I wouldn't have a perfect square because no two numbers together would, when multiplied together, would give you 3. But can anyone name another fraction that would be a perfect square? I'll give you the numerator. Numerator could be 4, right? Because 2 times 2 would equal 4. What can we put on a denominator? What do you think?
121.
121, and what's that?
11.
11, right? So it could be 2 over 11, because 2 over 11 multiplied by itself would give you the fraction that you guys were just proposing. Okay, so now this could be an exercise activity. I could say to you, determine if 25 over 49 is a perfect square, and is 0.4 a perfect square? Well, again, this is where a calculator comes in really handy. With a calculator, you could just see if the square root of 25 gives you a nice whole number. And it would. It would give you 5. Would the square root of 49 give you a nice whole number?
Yes.
What number?
7.
Right. So 5 over 7 times 5 over 7 would give you 25 over 49. Now what about 0.4? Would two numbers multiplied together give you 0.4?
Yeah.
What would they be?
0.2.
Right, 0.2 times 0.2, okay? No, wait a minute. No, it wouldn't. Think about what 0.4 is as a fraction. It's right here, 4 over 10, right? So now, how do we take 4 over 10 and think of its perfect square? Well, 4 is a perfect square, but 10 is not a perfect square. No two numbers multiplied together will give you 10. 5 times 2 gives you 10, but those aren't the same number. 3 times 3 gives you 9, but that's not 10. If I go up to 4, that's not 10, that's 16. So the reality, 0.4 is not a perfect square. Okay? It's not. All right. So a rational number that cannot be expressed as a product of two equal fractions is called a non-perfect square, right? So you have the perfect squares and the non-perfect squares, okay? So we talked about that. There are some numbers that when multiplied together can't give you that, but here are some of their properties, and this is what I was just explaining on the calculator. A non-perfect square, when you punch it into your calculator, will give you this big long decimal number. It's called a non-terminating decimal because there is no end to it, okay? So again, for example, the square root of 5 gives you this big long number, okay? The other thing you need to know is that value that you get on your calculator is an approximate value. It's not the accurate value because, I don't know, if I asked any of you to type that in your calculator, 2.236, and then multiply it by itself, you wouldn't get 5. You'd get a number close to 5, but not 5, okay? Because it's an approximate value. Your calculator is giving you something approximately close to a square root. Where it can, with a perfect square, like the square root of 100, give you the value 10. It can go, here you go, here's your square root. With non-perfect squares, it's going to give you some sort of an estimation on that. Okay, so let's try a couple examples. Okay, the first one let's just do it out loud. What's the base and what's the exponent of 5 to the power of 3? What's the base? 5. And the exponent? 3, right. That's the exponent, that's the base. Okay, question 2, somebody else. Who could tell me how you'd write that as a power? How would you write it?
5 times 5 times
No, this one. This one here, the 4. The base would be 4 to the power of, right, 4 to the power of 6, okay? And there's a simple one. How would we write that as standard form? 5 times 5, yeah. Which is, what's the answer?
Oh, 10.
No, 5 times, right, okay. Estimate the third power of 2. So what would 2 to the power of 3 be, approximately?
6.
No, not 6. 8, yeah. Common mistake. Let's all make sure we don't do that. If you see something like this, 5 to the power of 2, it's not 10, right? You're not multiplying this times this. That's not what a power means. A power means 5 times 5. Just like this one means 5 times 5 times 5. The power is different. It's the most common mistake that generally students do when they first start powers. What would this diagram represent if I was to write it as a math power? Anyone? What this blue diagram, what do you think?
2 to the power of 2.
2 to the power of 2. What's another way you could say 2 to the power of 2?
2 squared.
2 squared. Very good. What's the square root? Actually, first of all, what is the answer to 2 squared? 4. Right? Notice there's 4 squares. What's the square root of 4? 2, yeah. Okay, so you can see how it's all starting to hopefully connect a little bit. That's a simple example. So how can I write 10 as a power so that the answer equals 100? So 10 to the power of something equals 100. What would that something be? 2, correct, okay? Write in standard form 2 times 3. Actually, instead of that, what's the answer to 2 to the power of 3? And we already did that one, so it should be 8. Yeah, very good, okay? Write 4 as a power of 2 and draw a square to present it. Let's skip number 8. Now, number 9 is a very common type math question I've seen on grade 9 exams. Which is smaller or which is bigger? 5 to the power of 3 or 3 to the power of 5? Now, you could estimate both of those. You could mentally do those, or you could calculate those with a calculator. But think about what is 5 to the power of 3? What's the answer going to be? What is it? Okay, well, what's 5 times 5? 25 times 5? 125, right, 125. Okay, so be careful about mentally calculating this. I would recommend a calculator. What's 3 to the power of 5? Now, this is going to get harder. 3 times 3 times 3, it's going to get... Now, you may not have to do the whole thing to maybe realize that this one is going to get bigger than 125, but maybe you do, right? So again, I'm just going to turn on the light a little bit. Let's calculate 3 to the power of 5, just as another activity, again, to make sure how we could do that on our calculators. You want to use that y to the x button. 3, y to the x 5. Anyone got the answer? It's 243. So which of those is smaller is 5 to the power of 3, right? Because it only generated 125, whereas the other one generated 243. Very common question to see that kind of one, and you're going to see that one on the assignment today.
Giddy up.
All right. Yeah, that's awful. A word problem, okay? I've got a garden. I actually don't. I hate gardening. I got a garden, and it's a perfect square. The area of my garden is 25 meters squared. What's the length of one of my sides in my garden? What's the length of one of my sides? 5, right? That's right, 5 meters, okay? And here's a great example of why I'm only using the positive root here. It wouldn't be negative 5 meters. It's not like I would have no sides, right? All right, question, is 1.2 a perfect square? What's a way you could determine that?
Instead of writing 1.2, why not just take out the decimal and do it as 12? It's basically the same thing.
It's not quite the same thing. But my guess is this would be my easiest answer. So I'm going to type 1.2 square roots. Did I get a nice whole number? I got 1.095445115. Does that sound like a perfect square? Nope. Exactly. Okay? So calculator is going to be your friend for these activities. Be careful with estimations like that. If I did the 12 thing. Well, first of all, is 12 a perfect square? No. So that would also give you the right kind of clue, right kind of ballpark. But again, calculator is a very good friend to you in this. Okay, so let's wrap up by just comparing to what you need to know. Key concepts. Here's what you need to know in part 2. A perfect square can be expressed as the product of two equal rational factors. Okay? The square root of a perfect square will calculate exactly. Right? The square root of 100, 10. So if it's a perfect square, its square root will be calculated exactly. The square root of a non-perfect square, guys, can be determined using a calculator, and that the answer you're going to get from the calculator is not the actual answer, it's an approximate answer. So calculators for non-perfect squares are going to give you an answer close to the correct answer. If the area of a square model is a number, then the side of that model is the square root of that number. And again, that was kind of what we saw in the diagram there. So let's boil it down to even more simple terms. These are the 3 key concepts in part 2. What's a square root? What's a perfect square? And what's a non-perfect square? Now you'll notice there's one thing that's missing from that simple 3 things. I didn't put powers. I didn't say what's a power, what's a base, and what's an exponent, even though you learned about it. That's because we're going to revisit powers in a whole other unit. But you kind of need to know what they were in order to do a square root. So although I taught you what a power is, we're going to revisit that. This is what the actual math curriculum says again. We started with this. Determine the square root of a positive rational number that are perfect squares. Determine whether or not a rational number is a square number. Determine the square root of a positive rational number that is a perfect square. What's the error made in a calculation of a square root? The error, by the way, is that it's an approximation. Determine a positive rational number given the square root of that positive rational number. And explain with examples why a positive rational number has both a positive and a negative square root. Okay? This is what it says in the math curriculum. I hope that most of that is mostly clear to you. Again, don't overthink too much of this content. That was really the key, just that simple stuff there. Okay, so we're going to move from here into the other room. Just a sec, not everyone at once.